Welcome everyone to the second edition of the OHARS workshop. Thank you for being here. For today, we have two invited talks, one by Alexandra Altiano and the other one by Paolo Rosso, and 6 exciting papers.
Yeah, hello everyone.
Hi.
So I'll start my slide.
Great. Anno will presented an empirical analysis of recommender system robustness to Chilean attacks. Anno is a PhD candidate in computing with emphasis in computer science at Boise State University. Her research focuses on characterizing and mitigating misinformation in social media and online platforms by investigating the actors responsible for misinformation creation, spread, and the victims of such false information through the lens of linguistic, social network, and complex user behavior. So, when you're ready.
Yeah, thank you for the introduction. So can you see my screen?
Yes.
Okay. So hello everyone, my name is Anushresta and I'm a PhD student at Boise State University. And the work that I will be presenting today is about an empirical analysis of collaborative recommender systems robustness to ceiling attack. Recommender system is considered as a solution to support decision-making process among users by surpassing the challenge of information overload in online or e-commerce platforms. Among different recommenders technique, collaborative filtering based is the most popular one and commonly used in e-commerce platform. It provides recommendation based on users with similar taste. So due to its openness, collaborative filtering based models are vulnerable to shilling attacks, where malicious users create fake profiles so that they can then manipulate algorithms by providing fake reviews or fake ratings. Therefore, many studies have examined the vulnerabilities and robustness of collaborative filtering based models. But so far, previous studies in recommender system have characterized and modeled shilling attacks, defined new matrices to quantify the impact of these attacks, and applied a detect plus filtering approach to mitigate the effect of spammers on recommenders. However, these studies thus far has focused on assessing the robustness of recommender system through simulated attack. And it fails to provide evidence on what is the impact of fake reviews or fake ratings on real world setting. So in this work, we seek to understand the influence of fraudulent reviews in the recommendation process in real world scenarios. For this, we utilize the data from two widely used e-commerce platforms, that is Yelp and Amazon. We consider Yelp reviews from two domains, hotels and restaurants, and labeled user as a spammer if he wrote at least one review filtered by Yelp as spam. Similarly, we considered Amazon reviews from two domains, beauty and health. And in this case, we define ground truth based on helpfulness votes. That is, a user is a spammer if he wrote at least one positive review, but that is not helpful. So we focused our analysis on 5 well-known and widely used collaborative filtering based recommendation algorithms, namely item-item, probabilistic matrix factorization, alternating list squares, Bayesian personalized ranking, and Funk SVD. We performed a 5-fold cross-validation for each algorithm and evaluated the performance based on root mean square error and NDCG, which are classical measures for evaluating predictive and top-end recommendations. We also considered measuring explicitly defined to quantify the impact of shilling attacks on recommenders, such as prediction shift, which captures the average absolute changes in predicted ratings for attacked items, and hit ratio, which consider if the attacked items are promoted to the user's top end recommendation. The main contribution of this work is twofold. First, we seek to answer whether shilling attacks affect the robustness of considered recommender algorithms. And second, we investigate if there is a specific user group that are affected more than others by spammer. So to answer the first question, we analyzed the performance of widely used for collaborative filtering-based algorithm using these 4 data sets in presence of spammers, and then we compared them when spammers are removed. We did not use Bayesian personalized ranking algorithm for predictive measures, as it is top-end recommendation algorithm, and it provides scores to items but does not produce rating prediction. And by doing this experiment, we observed that after removing spammer, we have lower root mean square error score, which means better prediction, and increase in NDCG in majority of the cases. This means the users' preferred items are more likely to appear within the top 5 recommendation when spammers are excluded. So when spammers are excluded, we have both better prediction and better recommendation. Talking about the prediction shift, previous work has shown prediction shift values ranging from 0.5 to 1.5 when Chilean attacks are simulated. However, we observe very small value in real world scenario, ranging from 0.087 to 0.16, which might not be enough to promote or demote products attacked by spammers. So overall, we can say that the performance of collaborative filtering-based recommendation algorithm is affected by spammers ratings, but barely perceptible due to very small shift. Also, looking at the performance as a whole may not clearly quantify how much spammers are able to deceive recommenders or state if there are specific user groups that are affected more than others. Thus, we performed a more thorough analysis to understand a user group who are more affected by spammers. So to do so, we use fairness and goodness algorithm that provides a measure for capturing user rating behavior. It computes a fairness score for each user and goodness score for each item. And a fair user should rate an item with the rating that it deserves, while unfair ones would deviate from the value. And the goodness of an item specifies how much users in the system like the item and what is its true quality. So basically, this algorithm computes the goodness of item as the average of its rating, where each rating is weighted by the fairness of user, and the fairness of user is calculated as how far the rating provided by a user is from the goodness of the items. So higher the fairness, the more trustworthy the user is. And the fairness score ranges from 0 to 1, and goodness score ranges from 1 to 5 for 5-star rating. So to better understand which users are really affected by these spammers, we segmented users based on their fairness and identify mainstream and non-mainstream users. Here, mainstream users are the benign users whose rating aligns with what an item deserves, and non-mainstream users are the ones whose rating deviates from that value. So then we plot root mean square error against different fairness range. Here, orange line represents root mean square error when spammers are present, and blue line when spammers are removed. So it is expected to have blue lines below orange line. So to make it easy to understand, we highlighted statistically significant differences in performance when spammers are excluded. So looking at the difference here in table, we can see that regardless of the algorithm for both Yelp dataset, removing spammers reduces root mean square error for all the users, except in Yelp restaurant with alternating least square and Funk SPD for fairness range 0.4 to 0.5. But for Amazon dataset, when the user fairness is greater than 0.4, removing spammers increase the root mean square error score for all the users and for each algorithm. So This could be due to the rating distribution of spammers and benign users across these two platforms, where when we checked, we found that spammer and benign users rating behavior is similar in Amazon than Yelp. That is, majority of the rating provided by both spammers and benign users are 4 and 5. And therefore, removing the spammers could cause the recommender to lose some information from mainstream users. Whereas when we look into the Amazon users with lower fairness, removing spammers reduce root mean square error for majority of the cases and are statistically significant. Similarly, when we look at the trend of NDCG, we can see that the quality of generated recommendation are rarely improves in Yelp dataset for users having fairness greater than 0.5. Whereas Amazon dataset, the value of NDCG is higher when spammers are removed in majority of the cases, 28 out of 47, and independently of the user type. In addition, removing spammers also helps in reducing the number of attacked items that hit the top 5 recommendation for all users in all datasets according to hit ratio. So our analysis reveals that removing spammers in Yelp is beneficial for all the users when considering the predictive performance of algorithm based on root mean square error. And for Amazon, top N algorithm are the better among mainstream users according to NDCG. So we also observed that the performance of algorithm improves in terms of both root mean square error and NDCG score for Amazon non-mainstream user, which means non-mainstream users are more likely to be affected by spam ratings. And these non-mainstream users affected by spammers represents more than 20% of benign users, which would translate into hundreds of thousands of users in real world scenario who would not be equally satisfied by recommenders that are not robust to shilling attack. So to conclude, in this work, we took a deeper look into how shilling attack affect a recommender system in a real world scenario and conducted an in-depth exploration of performance of 5 well-known collaborative filtering algorithms on 4 different datasets, where we observed that users are exposed to better recommendation when spammers are excluded based on both predictive and top-end recommendation. We also explored the differences in performance between the mainstream and non-mainstream users, and we saw that Amazon non-mainstream users are the ones most affected by shilling attacks according to both root mean square error and NDCG. For the future work, it would be interesting to look at other type of recommender algorithms beyond collaborative filtering based algorithms to see if the trends that we observe in this analysis remains the same. And also we plan to test the effectiveness of adversarial training for recommender system under the real world attack that we consider in this paper. Thank you, everyone.
Thanks, Anu, for the presentation. Does anyone have any question? Remember, you can write in the chat or you can unmute yourself and speak. In the meantime, we have a few questions. How was spam distributed for mainstream and non-mainstream users? Did you find that non-mainstream users maybe rate items that suffer less attacks by being less popular?
That is the our finding. Like for mainstream user, so mainstream user means like benign users who aligns with the majority of the people who are rating that product. So mainstream users are that's why the mainstream users are not that affected, but the more effect is seen in the non-mainstream users who are not fraudulent, but have like different opinion about the item. Maybe they have like different experience or they did not like the product, but that doesn't mean that the product is bad. Yeah, if
Great.
that answers the question. Yeah.
Yeah, of course. And you were studying about the spammers. Did you think about to study other deliberate and probably more sophisticated forms of attacks?
Yeah, that is our future work, like adversarial attacks that has been like gaining a lot of attention nowadays. So we started with first we started with the real world scenario and then basic. So our next plan will be to look into these sophisticated attacks and then adversarial attacks.
Great. Okay, it seems that there are no more questions. Thank you, Anya, for your presentation.
Thank you so much for having me.
You're welcome. And now we continue with Mark. Yeah, you are there. We have the presentation to trust a liar. Does machine learning really classify fine-grained fake news statements? Mark Mifsud, sorry if I'm mispronouncing it, joined the University of Malta as a student for a bachelor's degree in information technology, focusing on software development. He's currently completing a master's in entrepreneurship. The paper being presented today reflects his interest in how people get deceived and the investigation of extraordinary claims. When you're ready.
Okay, thank you. Can everyone hear me? Okay, yes. So hello everyone. So our study to trust a liar is asking this particular question: does machine learning really classify fine-grained fake news statements? While there are many different studies in the realm of fake news classification, we have noticed a very common approach in the literature that where authors do something along these lines. They first identify an appropriate data set related to fake news, then they apply to it some natural language-based machine learning method, and then they would report their accuracy or some other metric, usually accuracy. Often they would compare their results to previous attempts, and that would be the summation of their study. We conclude in our study that this kind of approach, which is language-based for fake news detection, is not really adequate for detection. Accuracy alone is not a good metric. I hope to convince you of this by the end of this talk, and we would love for this study to start a conversation about what would a suitable approach look like if this is not. To better understand this study, it's best to split it into parts. So in part one, we just followed the same procedure and we built our own fake news classifiers. To do this, we used the liar dataset. The liar dataset is made up of short statements extracted from policyfact.com, which is a fake effect-checking website. These statements look something like this. They're this short, and they are classified according to 6 levels of truthfulness, ranging from true to pants on fire. That would mean that they are complete lies. For example, this particular sample here is labeled as mostly true. There is also detail about the speaker that is making the claim, like their state of origin, their political affiliation, their job description, and some other things. We did not use this data in our study, but virtually all previous studies that used this data set have used this particular data. What we did use are these numerical features representing how many statements the speaker uttered for each level of truthfulness, including this one. We call these features the reputation score. Other studies may call it something else. We call it the reputation score. There is also the context where the statement was uttered, and this also was not used by us. The liar dataset already comes split in portions for training, validation, and testing, and all studies use this particular split, so comparison between them is somewhat fair. So this is how we built our fake news classifiers. We used 3 differently sized language transformers, which were BERT-based, that is the smaller transformer, while Roberta and Albert are the relatively larger ones. And this allowed us to ask whether larger transformers perform better at this particular task. We also added a fully connected neural network to enhance the transformers classification. And the reason for this is that we used the speaker's reputation, which as we have seen is numerical in data. And language transformers are not particularly good at dealing with numbers, so this neural network segment was necessary. To see it on a diagram, first, a language transformer would perform classification using only the uttered statement. Then, to enhance the score, we take the speaker's reputation, and the fully connected neural network would take the output vector from the transformer together with the normalized reputation score to produce a final classification score. The result for this is that we achieve a higher accuracy compared to previous studies. But more interestingly is that we achieve this using only the statement and the reputation, while previous studies, virtually all of them used more data than our study did. In the paper, you can see more comparisons apart, not just against these, but against even more studies. This concludes the first part of the study, but the interesting part comes when we started to investigate what was really going on with these high accuracy models. The first question we asked was whether the fully connected neural network was biasing the results. To test for this, and we did this, by the way, because we had some suspicions that this was the case, we selected 226 entries that were either lies from mostly honest people or truths from liars. So these would be statements that go against the character of their speaker. And to make a long story short, we found that the neural network was prone to classify based on people's history rather than the statements themselves. The transformers did mitigate these behaviors to some extent, but there is no reason to assume that the transformer completely compensated for this particular bias. The second test we did was more focused on the language part, because we asked whether the quality of the textual data mattered. In other words, how much of the accuracy is dependent on the quality of the text. And to test this, we created two variations of the liar data set. One we called shuffled liar, which is of poorer quality, and the other one we called the cleaned liar, which is of better quality. Shuffled liar was created by literally shuffling the claims among all entries without changing any other attributes. So we just shuffled the statements randomly. And the reason for this is that if equal accuracy can be obtained on this randomized set, that would mean that the accuracy obtained on the original liar data set would be purely accidental. The story with cleaned liar is more interesting. This was done mainly because we found flaws in liar, and we corrected them manually. We found that 207 entries were not even claims at all, and we eliminated those. And we corrected a lot of spelling and other kinds of mistakes, like the ones you see here. So this data set is less noisy, or supposedly so. The results on these, the first thing was that the models did fail to adapt to shuffled liar. So this suggests that the results on the original liar were not purely accidental. There were also some slight improved accuracy scores on the cleaned data set. However, if we only observe the transformer-based classification, surprisingly, the classification on the cleaned data set was generally poorer, with only one transformer being an exception because it had a slight gain. This led to the question about whether or what was really causing the accuracy. And this led to the next question, which was, are these models really modeling deception or veracity? And this third test was pretty simple, but it was quite telling. We took one originally true statement, which was correctly classified as true, and we made variations of it where we either negated that statement or we reduced the probability of that statement by adding some mutually exclusive facts in the middle of it. And we even changed it into a contradiction. Now, this should not be labeled as fully true. However, all of these statements still classify as true. And this shows that the models are not really modeling deception or veracity and are vulnerable to adversarial attacks. The next test is where we asked, is fake news classification an ill-conditioned problem? Now, ill-conditioned problems are particular problems that are hard to solve in practice because their output varies considerably with gradual change or slight changes in their input. So to test for this, we had to test how much the classifications varied with gradual changes in input. That would be the test data. And to do the gradual changes in input, we used stratified cross-validation. So basically, we split the training and validation set in 5 similar segments, and we did 5 runs where for each run we used 1 segment for validation, and we did the training on the remaining 4 segments, and that would change the input gradually. We also repeated this task with a sentiment analysis task for comparison, and for that we used the Stanford Sentiment Tree Bank sentiment analysis data set. The result for this is that the sentiment analysis task, which is the first one shown in this chart, you will see that there are very smaller variations in there. Here, the mean variance shows the variation among the predicted labels, while the overall mean square error shows the variations of the results from their original target. All of these are averaged across the 5 runs. And you can see that the sentiment analysis by comparison is like 4 times more stable. And also, as a side note, the larger transformer even performed better on the sentiment task, where on the fake news classification, this was not the case. This led us to conclude that at least compared to sentiment analysis, this kind of fake news classification is much more unstable. We took this test one step further, where we pondered the question about whether fake news classification is not just ill-conditioned, but even an ill-posed problem. And in the paper, we argued a number of arguments why we think this is the case. Here, I will just present one stronger argument, which is that we find that there is no reliable indicator of deception in a string of text, where at least compared to sentiment analysis, by contrast, in sentiment analysis, you can find the presence of certain words or expressions that would make it easy to map that string of text to a sentiment. There is no equivalent information that is universally reliable in this manner for fact-checking. So for this and other reasons, we conclude that without the model having knowledge of the real world, fake news classification using purely natural language processing is very likely an ill-posed problem. Among our conclusion, we recommend that fake news classification requires using some model where that has real knowledge of the word. This can be done, for example, with knowledge graphs, although they are not a perfect solution. However, that would be a bare minimum for this task to be adequate. And we also recommend that the metrics should go beyond accuracy. As you've seen, our models were more accurate. However, upon more investigation, there were some visible flaws. And these are some metrics which we did in our test, but someone smart might consider some other ones. That's all from me. I thank you for your attention, and I surely welcome your question. If you're interested, all the code is available on GitHub, and feel free to check it out. Thank you.
Great, Mark. Thanks for your talk. We have a question in the chat. What do you mean by shuffle the claims?
Very good question. What we did was that this probably explains it better with the graphic. We took the statements and we literally used the spreadsheet program to shuffle them around, and we randomized their order and without changing any other attributes. So we literally just mixed them up, and that's all that was done here. Does this answer the question?
I think so, but I'm not sure. So you didn't change the order of the words within the statement, only the order of the statements in the training set?
Yes, we changed their position with respect to, so we ended up with a statement that does not belong to its original speaker, really. And also it does not.
I see. So you moved the statement as if it's coming from a different speaker, and yes, maybe it has a different label or something like.
Exactly, yes. And more importantly, it also gets a different classification score. And so we wanted to check whether this would still give us the same accuracy, because if that was the case, then the accuracy on the original set would be accidental. And we suspect that this was not the case because we found that there were some repeated some claims were repeated more than once, and we have some reasons to. We have some good reasons to assume why this did not perform so well. Basically, the reason for this was that we found that there were many claims, for example, like 10 or 12, which were all about whether Obama was born a Muslim or not. Now, all of these would be rated as false. And in the original liar data set, all of them would have the label as false. Therefore, the language model would eventually learn that, listen, whenever you see Obama and Islam, just say that this is false. When we randomize that, the language model would fail to see that association because of the shuffling, and therefore this model would perform much worse. Next question.
Did you consider how to model the context of users? For example, the users that were making the statements?
The reason why we did not use the users was because we found that we suspected that there was no real usefulness to decide whether a statement is true or false, depending on the name of the speaker. It doesn't really matter whether someone is named Richard or Daniel when a statement is true or false. So that is the reason why we did not use that particular data. However, we thought that the history of the particular speaker would be much more important for determining the truthfulness. So that is why we use that part.
Great. And well, we see that sorry,
okay.
yeah, Shiri.
Sorry, no, I had the question in the chat, but I also wanted to, I raised my hand separately, so I'm kind of doubling up. But Mark, first of all, just thank you so much for this wonderful talk. I really appreciate the detailed analysis, and I look forward to reading the paper in greater detail and seeing the code, etc. So my question for you is, and I think that this is a challenge that we're facing in the misinformation space, is, when you define the problem of fake news detection, how exactly do you define it? Because I think that the choice of like you said, in some sense, it's related to what you said, but kind of taking it one step further, is that if you choose to detect whether the entire article is false, whether a particular sentence or claim is false, or whether maybe the entire website, like domain of the website, is a disinformation source that is intentionally pumping out false stories, those are each kind of different problems to solve, and they require different approaches. So I'm curious, how can we, if you have thoughts, how can we as a field clarify and specify better which of these kind of sub-problems are we trying to solve, instead of using this umbrella term fake news, which is also co-opted in various ways to discredit true media. So, we need to be a little careful, I think, about how we phrase these challenges.
That is a very good question. When we say fake news, here in this study, we use just short statements, but as you are well saying, when something is fake news, it can be in many forms. To better classify it, the simplest way to do that is to say that fake news is false information with the intentional purpose to deceive, usually for some gain, which is either political or monetary or something like that. And if you frame it that way, if this is a false statement, then by definition, the only way to determine that something is false is not by analyzing the style of how this was spoken, but by literally have the model and the computer model have defects of the real world. If I may, related to this is how some previous studies attempted to identify fake news based on the style of the language, and you will find, for example, that if the style of the text was informal or if it lacked specificity, then it was likely false. However, this is not a universal truth, because you can have something written informally and yet
I agree
completely true. So
yeah, this is very outdated, even though it's only from 2018, but it's actually based on an outdated understanding, I think, of disinformation. And
yes, and even a very dangerous one.
Yes.
I think the upcoming talk by Paolo Rossi will probably illuminate us more on this subject. So shout out to Paolo from here.
Happy to have more conversations offline, but just to make a small note. So in my work, including in my startup as well as in my lab at the University of Connecticut, we're moving specifically away from using the term fake news, and we're using disinformation instead, and that is by design, because the term fake news has become a catch-all that is actually meaningless, because it's being used by politicians to discredit real media. So it becomes kind of a liar's dividend thing. Oh, I'm being blamed for something. Oh, that's fake news. Never mind. Don't listen to them. They are fake news. So we're intentionally now using disinformation. And I cannot speak for others, but I kind of encourage others to move in that direction as well.
Yes, I think it's a good. That's a good point. I mean, it's a better definition. As you say, just misinformation.
Thanks again. Really looking forward to checking out the full details.
Okay, great. If there are no more questions, we can go to the last presentation of this session. Thank you, Mark. So, Masa, are you there?
Masa, yeah.
Masa, thank you. Okay, Masa will present at Paris Polarization Award Recommended Interactive Systems. Masa Badami received her PhD in Computer Science and Computer Engineering for the University of Louisville in 2017 under the supervision of Professor Olsa Nasraoui. Her research includes the causes of bias in data and algorithms, define and applying measurements of fairness, developing data collection and modeling methodologies aimed at creating fair algorithms, especially in polarized environments. So Masa, when you're ready.
Thank you so much. Let me share my screen.
Great. Let me know if you can. Yeah.
All good?
Awesome. All good.
Awesome. Thank you so much. Hi, everyone. My name is Masa. Thank you for joining me for this talk. Today, I'm going to talk about our proposed method, polarization-aware recommender interactive system, aka Paris. Okay, let's talk about the motivation. A lot of online platforms automatically filter or sort the order of items on a user's home feed, in many cases without an explicit request from the users to do so. As information filtering algorithms become more and more targeted and selective in filtering what users see and discover, one important question arises, which is, could these algorithms filter too much information? Especially in the case of polarization of interest or opinions, it can have very serious consequences in real life, particularly on social media, because the users, they can get locked in an online platform as they interact with filtering and recommendation algorithms. So as we all know, this can bring us to disinformation, hate speech, and confirmation bias, etc. It can reinforce the polarization in such environments. This is important. This is very important to understand how machine learning algorithms, especially recommender systems, behave in a polarized environment, because we want to have recommender systems that they are effective, efficient, especially in the presence of a set of polarized items. We all know that over a specialized recommender system, they can prevent individuals from getting exposed to the opposing views. And what we would like to do is to allow users to discover different viewpoints, which can allow them to discover diverse perspectives, and that these perspectives are less limited by the filter bubbles. So our goal is to focus on items that they can cross polarization boundaries. And we would like to reduce the user's chance of getting locked in an online platform as they interact with that filtering or recommender algorithm. We would like to provide user control counter polarization parameter, which acts like a discovery dial to give the user the freedom to tune the severity of their filter bubbles as they wish. One thing that I would like to mention is that whether humans prefer to discover more or less items is beyond the scope of this research. This is something as a disclaimer. So let's dive into the counter polarization in recommender systems. The first step is defining polarization score. Basically, polarization score is an item is polarized if there is a gap between opposite concentration poles and the peaks of the histogram of all the user's rating. We can compute this polarization score for each item based on an approach that is presented in one of the recent papers. So in order to have a good recommender system, the specific application domain and recommendation goals should be taken into account when deciding an algorithm. For example, for a user, recommending popular items might provide valuable reminders, but the thing is that it could be it could add a little value because it's just like popular item, not necessarily the relevant one. So our goal is to design a recommendation system which not only include the relevance of the item to the user's interest, but also in case the user is interested, it can include the opposite view as well. So for our polarization aware recommender interactive system, aka Paris, our goal is to design a recommendation system. As we talked about, it includes the relevant items, and also it includes the opposite view in case the user is interested, so it can increase the user satisfaction overall. To do so, we are using our good old friend, non-negative matrix factorization, since it has shown good predictive accuracy, flexibility for modeling various real-life situations, and also it can incorporate additional informations. So we are particularly interested in the latent space. So I'm gonna explain a little bit about the intuition behind that. So here we have the user item latency space, and technically the recommender system, they find the nearest or like the most relevant item to the user in that latent space. What we would like to do is bring the user and the other content a little bit closer so it can be also shown to the user. Recall that in the classical problem of non-negative matrix factorization, we would like to decompose a non-negative data matrix into two positive components, right? So to do so, we are gonna predict the overall rating by minimizing this objective function. The issue is that the item rating alone is not going to be able to fully consider the polarization. So what we're going to do, we are adding the second component to that. So this is what we propose to minimize as the our objective function. We added this user discovery factor, which is set by the user, and basically the first part would be the item relevance, and the second part would be regarding the polarization score of the environment technically. So we are considering both of these in order to compute the new rating. So we are adding users average ratings, as we can see here. And then what we're going to add is consider basically is the item gap ratio. So GI measures how extreme the different viewpoints are. And the next one that we are adding is the polarization score for that specific item that we want to see whether to show or not. And then at the end, we are defining this user preference threshold, obviously, which can set by the either by the user, or it can set by the model designers technically. For all of our math enthusiasts, here are the new incremental stochastic gradient descents equations that they update after each iteration of the recommendation. Now let's dive into the experimental results. We tested our proposed approach on a simulated scenario, and we are generating rating environment with about like 50 users and 200 items, which the items are evenly divided into opposite viewpoint sets, and we have two sets of groups. So these items, they are like, for example, blue and red, and we are defining two groups. That in group A, the users, they like red items, so they give like higher rating that threshold, and in group B, they like the blue items, and they give higher ratings to that group. So this is how we define our environment as a multi-user fixed environment. We also generate this environment with different values of polarization gap and user discovery factors for our experiments, which I'm gonna show the results for those. So for simulating this interactive environment, the user will give a rating for only one item of the selected for one of the selected items, and we take this rating value from the true source of the ratings, for example, the ground truth data, and we repeat this process about like 100 times, because there are like 100 unrated items for each user to simulate an interactive recommender system scenario. So for each iteration, we measure MSE and other metrics, which I'm going to talk about in a bit. So let's take a look at traces of this interactive recommender system with the classical NMF recommendation algorithm. So as we can see here, gap is 0, which means the gap between red item ratings and the blue item ratings is 0. And as we can see, this is shown, this is the traces for the user who likes red items more. And as we can see, the recommender system, it shows the red items fully to the user, and then once it's finished, then it's gonna move to the blue items. And now if we increase the gap, we can see the gap like clearly it increases. So if we increase the gap even more, which is this environment is highly polarized, and it's like extreme likes and dislikes towards red and blue items. And as we can see, when we use NMF, it keeps each user in the safety of the preferred viewpoints, even if the gap is 0, let alone when the environment is very highly polarized. But when we apply our proposed approach, the Paris algorithm, as we can see, for example, for gap 0, we see that there are some blue items that are shown to the user as well as the red items. So we show the items that they are relevant to the user, but we also once in a while we show blue items to the user because the user decided to do so. So we are exposing the user to the other viewpoint. As we can see, we can see some fluctuations in the errors for each iteration. This is totally fine because like we have two objective functions that they are struggling against each other to show the opposite viewpoints, basically. For continuing our experiments, we are using two evaluation metrics, MSE, and there is another one, opposite view hit rate, which technically measures whether the opposite view items has been shown to the user or not. So to make a more comprehensive evaluation of performance of our proposed method, we repeat the experiments with varying the parameter lambda, which is the discovery factor technically. And we use two scenarios. For one of the scenarios, lambda is same for all of the users. And for scenario B, only user U has lambda that is not 0. So basically we are saying that everyone else, they don't want to get exposed to the opposite view, but user he or she would like to get more discovery. So as we can see, when we compare it with classical NMF, classic NMF never gets exposed to the opposite viewpoint, but as we increase lambda, the user get more items from the opposite view. MSE, as we can see, it increases, but it's only because MSE is not a good metric to measure in these scenarios, because technically when the user gives the rating, the algorithm thinks that the best way, the ground truth is basically, it was supposed to be a red item, but we showed the blue item. So basically what it does, like MSE changes and it doesn't know about the user feedback yet, if that makes sense. So it's not the true measure, but we wanna show how it looks like in a fixed scenario. So to conclude our work, we proposed a polarization-aware recommender system that succeeds to broaden the viewpoint spectrum while maintaining the relevance. It's very important. It doesn't only show the most popular item, it still keeps the user's interest into account. So it allows humans to remain in or regain control of algorithm-induced filter bubble traps. It focuses on items that can cross polarization boundaries, not any item. So it's very important. We just don't randomly select something to show. So we show the most relevant item from the opposite view. And it has the ability to recognize polarization patterns that can arise during incremental optimization. For example, let's say the environment is not polarized, but because we measure and update that equation iteration after iteration, if the polarization happens in between of the recommendation process, we can still manage that. For our future work, we would like to extend our experiments to real users and also include other diversity metrics to show how showing items from the opposite view would play along with other diversity metrics. And by that, I'm going to open the floor to questions.
Okay, thanks, Mata, for your great talk. Does anyone have any questions? Okay, I have one. So on your evaluation, you assume that polarized ratings represented items that could break the filter bubble. So how can you be sure that divergent ratings also related to polarized elements?
So what do you mean that it's relevant? So
sorry?
What do you mean that how it's relevant? Like, are you talking about like the MSE convergence?
No, just about how can you be sure that divergent ratings are also related to polarized elements? I mean, how can... Yeah,
there's no way that you can be sure about, but we are only talking about the environments that they are highly polarized. So for example, any news that is controversial. So we already know that the environment is polarized, and like there are like other approaches that you can run on like test sets or the environments, and it would tell you what is the percentage, how polarized the environment is. So when you are, we are specifically talking about like those environments for this talk. But yeah, if there are other environments that they may include other things as well.
Great. Okay, so we are running out of time, so we'll allow for one more question. Shiri, if you want to talk.
Well, I suggest to give the floor to Anu, who just posted something in the chat. I can take it offline.
Okay, Anu asks, since it will recommend based on user interest, will that negatively affect the serendipity of the system?
Yeah, it would. Like for example, for our future work, this is another thing that we would like to measure, that how it would change the serendipity of that. So it totally changes that one as well and affect it in a good way, I mean.
Okay, great. Thanks, Masa. Thanks, Shiri.
Thank you so much.
We will be now starting our break. We will return in 15 minutes for the other invited talk by Paolo Rosso. Thank you so much.
Thank you.
Okay, welcome to this second part of the workshop. Now we will have the keynote of Paolo Rosso. Paolo is a full professor of the Polytechnical University of Valencia, Spain, and he's also a member of the Pattern Recognition and Human Language Technologies Research Center. And his research interests focus mainly in auto filing, irony detection, opinion spam detection, plagiarism detection. And since 2009, he has been involved in the organization of benchmark activities at CLEF and file evaluation forums. And he has been involved in the organization of several shared tasks in these topics. So welcome, Paolo. I'll let you then.
Okay. So thanks for the introduction and thanks for inviting me. I will be focusing my keynote on two aspects of harmful information. Well, fake news and conspiracy theories from one side, and from the other one, with respect to hate speech, I will be talking a little bit about misogyny, so hate speech towards women. So yes, it's true. This is a fact. We shouldn't talk about the fake news, but because it's somehow fashionable, because this is the name that is used sometimes by politicians, and these are the ones who decide, in many cases, to give projects on the topic. So we make all this mistake to keep on referring to fake news, but actually we should distinguish between misinformation and disinformation. So when false information is not necessarily intentional, and when instead it is, because there is the aim to harm someone. So I will be sharing with you mainly, okay, the time is kind of limited, so I will be mainly focusing on what we did here together with some colleagues, PhD students and postdocs, on credibility detection, first of all, and then I will share with you the way we address the problem, considering also emotion and multimodality. So this is something that should be included in the loop. Briefly, I will mention also something about the important to know something about the users, and not only the source of the misinformation or disinformation, but also the user herself. So we have worked a little bit on the profiling fake news spreaders and also conspiracy theory propagators. And in the last part of my talk, if I don't talk too much, I will address also a little bit the problem of hate speech, and as I said, mainly misogyny identification. Right, so misinformation, sorry, and disinformation, I mean, is not something new. And this happened also in the past, that some false information started circulating, like when Orson Welles said that that there was an alien attack on the radio, and someone believed it, even if it wasn't really said with the intention to harm anybody. But in other occasions, we should have a talk already about the disinformation, because this false information was made circulate in order to destabilize, for instance, king or politician and so on. And so this is the case also, of course, nowadays. There are, web pages and platform and sites where actually, the false information is made in with the intention to be satirical, maybe. But no matter that, always there are people that believe some of this news as a true, because they start circulating, you know, on the internet, and sometimes this is the case. On the other hand, as I said previously, there are many cases in which this false information is made circulate intentionally with a good timing, maybe before a presidential election, like it happened for Macron in the 2017 French presidential election. And so the focus is completely different, because in this case we can talk about harmful information, because the intention is to harm someone. In this case, precisely the French candidate. And of course, it's also important from a net viewpoint, because we are exposed to this, what has been called recently infodemics. So a lot of, rumors, conspiracy theories. So not false news, false information circulating, but actually, a narrative. In case of a conspiracy theory, there is a narrative behind. And for instance, with respect to COVID-19 pandemic. And this had, as you know, effect on the health of people, and some people also died, for instance, for drinking hand sanitizer with the hope of getting rid of the virus, coronavirus. So indeed, false information, disinformation, that is the one that we are more interested in detecting, because of the intent to harm someone, is really a problem, and this is perceived as so also, for instance, in the European Union. And there are 8 hubs in order to fact check information. And so these hubs are organized, let's say, by the European Digital Media Observatory. We are in one of them that covers Spain and Portugal. So many institutions, not only university and not only computational linguists, but also, a journalist, fact checkers are involved in these labs. In our lab, the iVerifier hub, 23 are the institutions that are involved. We just had the kickoff meeting a couple of days ago, so we just started. What is the problem? We are kind of aware of, but how this is really a problem, and how is it so difficult to be actually addressed, and why false information in general is difficult to be detected. Because there are studies that we are not so good as a human being to detect deception. So there were studies, for instance, over 1,000 participants, and few experiments were carried out, and the accuracy of humans, that those people that were able to detect deceptive information was a little bit over 50%, as you can see. So we are not very good. And moreover, we are kind of easy to be influenced by, by our surroundings, what is called the bandwagon effect, and we like somehow to receive information that is in line with our beliefs, what is called a confirmation bias, or something that actually we like. And so desirability bias, and moreover, if we are exposed many times to a news at the end, maybe, I don't know, for tiredness. I mean, we have the tendency to believe to this false information. So what is called the validity effect. So the problem itself is pretty difficult also for us, not only from an automatic perspective. Of course, even if now, I would say, unfortunately, because every time we are more exposed to false information, so now is really, I mean, a trendy topic. I mean, trying to detect the false information, especially disinformation. This was done from an automatic perspective since a while. For instance, there are very well-known works like the one of Castillo and colleagues that started to work on Twitter in order to see if to what extent it was possible to detect credibility. And so basically the first works, what they did, monitor what was going on in Twitter, if they detected some burst with respect to the frequency of certain keywords, then okay, basically they query Twitter in a time window around this burst in order to collect tweets and to with respect to a certain number of topics that they had to annotate, often via crowdsourcing platforms, and they then had to decide how to represent this textual information on the basis of what features, so message-based features, the existence of special characters, the sentiments, or the user-based features like number of followers, the followees, etc., topics, also some propagation-based features, so the depth of a retweet message, for instance. And of course, we are talking about the pre-deep learning era. So the first experiments had been carried out using pretty standard machine learning approaches, so classifiers like decision trees. And results weren't so bad, actually, in terms of F measure above 0.8. So what's happening now? Okay, I mean, what happened already before, but now every time there are more news circulating in Twitter. There is a very interesting work by Rosugi and colleagues that was published in Science 3 years ago, and I mean, they empirically demonstrated that false information is retweeted by many more users and spreads far more rapidly, especially when it has to see with political news. And moreover, they carry out experiments and they, as intuitive, I mean, they show how important is the role that emotions have. In case of false information, especially emotion like surprise, of course, but fear and disgust are a trigger. And so it's very much important to take into account emotions in the loop, in our systems, when we try to address this problem. This is what we did. Of course, I mean, it was 8 years after, so we were already in the deep learning era. We use LSTM, and we consider also, I mean, the emotional signals. So we came up with 3 slightly different architectures based on LSTM, where emotions were considered or on the basis of a lexicon, on the basis of a lexicon that contain also the intensity of these affective words, or considering a system that was pre-trained already with similar information. We carry out some experiments on claims from PolitiFact, and just the takeaway message wants to be that actually, if compared to the simple deep learning approach, having included in the architecture the emotions, even if in three slightly different ways, help in order to improve a little bit the performance from a statistical significant perspective on two data sets. Okay, of course, this is not always the case that the one variant is the best one, but on overall, one way or the other, or considering just the emotional lexicon, or considering this pre-trained system with messages that had been tagged already with emotions, well, one way or the other, it was possible to improve the results. And of course, this is not the only way to incorporate affective information in a deep learning based architecture. With a PhD student, a former PhD student, we were interested in addressing the problem of misinformation in general. So we carry out on some experiments on a data set that consider also satirical news. So, I mean, in this case, there wasn't really the intention to harm anybody. But yes, I mean, the information wasn't true. And so we carry out experiments on news articles on Twitter, but considering this, in this case, different categories, also including misinformation, so satire, hoax, propaganda, clickbaits, and of course, real news. And in this case, we consider a more effective lexicon. Once more, we had the LSTM-based approach model that received the textual information via word embeddings, and then it was incorporated this affective information. And once more, what can be appreciated that comparing with the results obtained with the proposed model, allowed to improve results on both the data set on news articles and tweets than the ones that were obtained by LSTM and the other baselines with a logistic regression or super vector machine. So again, the takeaway message is this one: emotions are, people who write false information, disinformation, play or wanted to play with our emotions, right? To surprise us and to trigger disgust, fear, and we experienced that during the coronavirus period, and so they have to be taken into the loop. In a follow-up work, the former PhD student actually showed that different emotions are triggered, or maybe are usually triggered in different parts of a text, especially at the beginning. Okay, we have an example there. So sadness, fear, and because actually is reading the headline or reading the beginning of a message that we could receive, I don't know, in WhatsApp, is when is in between quotes important for the person who started making circulate this false information, this disinformation, to trigger certain emotions like the ones I mentioned. But then later on, not necessarily the same emotions are triggered, as you can see in this color, colorful text. Another takeaway message that I would like, something that I would like to stress is that, okay, textual information is important, of course, but we should also consider, the images, for instance. And especially nowadays, every time more, we receive, for instance, memes. So it's important to consider also the image. And this is what we did in a very simple way. There are, of course, pre-trained models now. Pre-trained visual transformer, visual BERT, etc., that could be used. But what we did, we wanted to consider not only the textual information. For instance, with word to back, we wanted to extract the most likely caption to the image with 5 in this first work, 5 pre-trained models, VGG16, VGG19, etc., etc. And then we also wanted to calculate the similarity between this most likely captions that describe the content of the image and the textual information. So calculating the cosines between the word embedding, word to back, and these tags, plus other features, visual features or sentiments. But this is the core idea. And then we use neural network to, in the end, classify this news as fake news or not. We carry out experiments on 3 data sets, and even if not always the best combination of the features was the same one, as you can see, is on the 3 data sets, not only the textual information help to discriminate the news between true news or fake news, but also the similarity between the tags and extracted and the textual information, or the textual information of the tags themselves and some visual information. So again, it's important to consider not only textual information, but also the visual information that could be associated by a link, for instance, to image or an article that contains an image, one or more. And actually, in the follow-up work, we consider up to 3 images. In this case, we simplify things a little bit. We just focus on the title because it's actually where certain emotions are triggered. The title wants to capture our attention, so we use a BERT approach, a BERT model, a transformer, and then once more, even if in this case we use just VGG16 because it was the one that gave us the best results. Then we also calculated the similarity between the tags extracted by this pre-trained model on pre-train on the ImageNet corpus and the title itself. So also in this case, it was possible to see that better results were obtained in comparison to just simply using LSTM, for instance, or BERT or some state-of-the-art systems. So yes, I mean, it's important, definitely, even if it could be done in a different way, but it's important to take into account also visual information, images. Right, let's say something about the propagation of fake news, because of course, fake news, disinformation, okay, let's be more correct if you want, and the conspiracy theories don't propagate on their own. We often could be also responsible for propagating some of them, passing WhatsApp, passing something, some information without fact-checking its content. So it's important, as you can imagine, first of all, to have a look on at the source of the information, so where it comes from, if it is a site I know, or in case of a person, it could be important to profile this person in order to see if in the past the person was keen on spreading some fake news. This is what we did in a work where in this case we use, I mean, we obtain better results with convolutional neural networks, but what is important and what I would like to stress is that it's not only, I mean, important to use in many cases deep learning based architecture, because these models are the ones that allow us to, I mean, to obtain good results. But then in terms of interpretability of the results, is important to understand what actually happened. And so that's why, on top of using the textual information via word embeddings, we also incorporated in the architecture some psycholinguistic information, and we had some linguistic patterns and also personality scores of the users. Right, with respect to the linguistic patterns we included in the architecture, I mean, we extracted some of them from Luke, like, you know, pronouns, I mean, the cognitive processes, categories, causation, discrepancy, tentative, etc., affective processes, and with that maybe could be somehow interesting, the personality scores. We rely on a big five, and we rely on some previous work where basically, I mean, it was provided word embedding for each of the 5 traits. So it was a matter to see, I mean, the similarity between the text written by a certain user and the word embeddings of the 5 personality scores. And these word embeddings contain especially adjective information. And what can be appreciated that actually the best results, even if, I mean, in terms of F-score, as you can see, results are not, I mean, are not very high. The problem is not easy, but were obtained, the best results were obtained incorporating, integrating in the architecture also this component, so linguistic patterns and also personality scores. We also organize a shared task at the Pan Lab, if you know it, with the aim to see if it was possible, to what extent it was possible to profile fake news spreaders, just taking into account textual information, both in English and Spanish. Okay, I don't have time to go in detail. So if someone is interested, of course, there is the overview paper. because I would like instead to talk about, yes, spreaders of conspiracy theories. And I mean, the very preliminary experiments we carry out with the intention to profile them. So we work on Twitter data, we collected the tweets on the basis of hashtags that refer to, conspiracy theory, like anti-vax, like flat Earth, like NASA fake, like etc. Many more. And also, I mean, we consider hashtags that were used by anti-conspiracy people. And so we first, before carrying out some experiments, we had a look at the data set, and we noticed some kind of expected figures like propagators, so conspiracy theory propagators have usually less followers, and non-propagators have old accounts. Propagators tend to use more swear words. So you can see the link with the other side, let's say, of the harmful information coin. So not only disinformation can harm, but also, as you know, hate speech. And there was a trend by propagators to use swear words when they didn't succeed in convincing someone to follow their conspiracy theories. And moreover, on average, in their text, in their tweets, in this case, they talk more about religion. And actually, this, I mean, this could be noticed also in relation to what happened in the US and with Donald Trump, that he was considered to, I mean, to be there to save them, sent by God in order to save them from what could have happened in the case of Biden could have won. On top of that, we carry out some experiments, once more considering some psycholinguistic characteristics, and once more, yes, the best results were well, not the line is not correct. Is should be the previous one. So the best results were obtained with psycholinguistic characteristics. So not only once more a deep learning architecture like CNN in this case can provide the best results, but in many cases integrating in the architecture of the deep learning based model actual some psycholinguistic information or some emotions, or as we have seen previously, some images can actually, in case there are in the data set, in the information, in the textual information, actually can help improving the results. So yes, now in maybe 5 minutes or so, let's say something about the other side of the coin. So I like very much what the Wordley and colleagues define in terms of information disorder online, and actually what is considered harmful information, as we say since the beginning, is disinformation, because there is a real intent to harm someone, not in the case of misinformation, and then speech. And we carry out this year at PAN a shared task where, with the same aim of the previous year, the attempt was relying just on textual information to profile haters. both in English and Spanish. Of course, if someone, some student, some colleague would like to use these data sets to carry out some experiments with their students, of course, you can ask for them via Zenodo, no problem. What we did with some colleagues in Italy some years ago, talking about the hate speech, was organizing a shared task at Semeval, where the targets of hate speech were immigrants and women. So since the beginning, we thought, of course, I mean, they are not the only targets. There are other very important social groups that are a target of hate speech, but we focus on mainly on these two targets. And we were interested in seeing if always hate speech, so hateful messages were somehow explicit, so aggressive, or not, because sometimes, as it was said already today, the hate speech message could be implicit in case of using, for instance, stereotype. And then we were interested to see if the target was just an individual or, I mean, the social group itself. I'm not going to show you the results, things like this, but I mean, the details of the approaches, but what could be somehow interesting is to have a look at the statistics of the data sets, the two parts, the one about immigrants and the ones about the hate speech towards women. So, okay, I mean, of course, a speech is a problem, but I mean, fortunately, it's we don't, in a real scenario, we wouldn't have to face a nearly balanced percentage of cases, but I mean, with in mind, you know, machine learning, deep learning approaches, we try to come up with a nearly balanced data set. But what could be interesting is to see the difference with respect to the target. So in case of the immigrants, I mean, the target in majority of the cases, both in English and in Spanish, is the social group. So the target of the hateful messages. And majority of the cases, the messages were explicit. So, I mean, it was possible actually to detect a certain level of aggressivity. But if you have a look at the light blue, actually a lot of them were not aggressive. So this means that maybe in many of these cases, stereotyping was used, more difficult to be detected because more implicit. And in the case of women, instead, the target was mainly a woman, a concrete woman, not the social group. And okay, in this case, in English and in Spanish, I mean, it wasn't exactly the same in terms of the usage of aggressive messages, much more aggressive in Spanish and less aggressive in English, at least in this data set, but we cannot speculate, and some more studies should be done also on other data sets. With respect to hate speech against the women, we were very much interested with some colleagues in Italy to know something more. So not only focusing on if whether a message was misogynist or not, if the target was an individual or, you know, the social group, the women, but we wanted to understand this misbehavior. I mean, so we, on the relying on the previous studies, we propose a taxonomy of with 5 types of misogyny. So derailing, dominance, discredit, stereotype, talking about the stereotypes and objectification, and the sexual harassments and threat of violence. And we don't have time to discuss more, to say anything about the results. There are the overview papers, of course, if you are interested in the topic. What instead I would like as a takeaway message to underline is the importance to focus once more on multimodality. So memes are used every time more, especially with respect to speech and misogyny. And so that's why we are organizing at Semeval a multimodal, with the U and not the O, multimodal automatic misogyny identification task. And then moreover, what is important to stress is to come up with a counter narrative. So to educate the people with respect to the not using the stereotypes and not having prejudices. And so there are works that try to do it in an automatic way. So every time I don't know, a hateful message or a stereotype is used against immigrants, okay. I mean, also some positive news about immigrants is highlighted in order to try to educate, especially youngers, that I mean, yeah, the word is not just black and white. So identify stereotypes is very much important because often they convey implicit hate speech. And recently we started addressing the problem of identifying stereotypes not only versus against women, but also against immigrants. And we try to identify them on the basis of a context, so a frame, if they are considered a threat, collective, personal, or if they are considered a resource, maybe from economic viewpoint. And also we consider positive stereotypes, because not always stereotypes are negative towards a certain social group. So basically, this is what I wanted to summarize in 35 minutes or so. Most of the work was carried out in the framework of a project, a national project on fake news and hate speech, and recently also in the framework of this hub on disinformation. So thank you very much. If you have some question or some suggestions, I'm open to them. Thanks.
Thank you very much, Paulo. If there is some questions, please use the chat. In the meantime, I have some questions for you about the what your experience working with languages other than English, because you are using psycholinguistics and emotions, and for extracting those features, many times you are relying on lexicons and which are well developed for English, but for other languages are not so much. So what do you think about that?
Yeah, well, this is always a problem, because if you come up with some new ideas, you have to compare with the state of the art, and most of the work has been done in English. So that's why it's important, of course, to work on English. But that is also why we try every year to organize shared task at PAN, both in English and Spanish, because it's a way to provide the researcher community also, I mean, that data about the problem of fake news spreaders, about the problem of haters, also in Spanish. But yes, it's a fact that many of the resources are in English, even if there are Spanish translations of Duke, of other resources, but not always, indeed.
Okay, Olfa, would you like to do your question?
Yeah, thank you. Thank you so much for this really amazing keynote, going over your rich history of research. It was very informative, Pablo. So how well would models trained on immigrant or misogyny stereotype detection possibly transfer to different contexts? And I understand language already is a barrier, but if we could somehow resolve the language, how just your experience in terms of, the differences in the text,
Okay, so you mean if a model has been trained on, in terms of identifying stereotypes about the women, how well would work in identifying stereotypes about immigrants?
No, if we fix the same, if we fix the category, right? But we move to different countries.
Okay.
Yeah.
Well, I speculate, but we didn't carry out experiments from this perspective, but it would be definitely interesting. For instance, with respect to the last work I mentioned about identifying stereotypes against immigrants, we work with transcript of the Spanish parliament, and so not with social media data in this case. And the best results were obtained with Beto, so the Spanish version of BERT transformer. Would be interesting to carry out experiments, who knows, with, Daniela is there, with transcripts of the Argentinian parliament, but yeah, there is the work that should be annotated following the same taxonomy. So actually, who knows if Daniela and Antonella are interested in this line or some other researchers, for in other countries also would be interesting, but there are no other data sets and annotated with this recent taxonomy. And as far as I know, there aren't any. Oh, hello, how are you doing? Younger researchers there. So yes, I cannot answer your question. I can say that it would be very much interesting, yes, to see how different or similar stereotypes could be conveyed in countries that share somehow a similar culture, but a different country.
Thank you.
Okay. Shiri, would you like
to
Shiri.
Yes, hi. I am here along with this, as Paolo said, young researcher, very interested in misinformation and hate speech. But, thanks for the great talk. And I really appreciate you tying together the problems of misinformation and hate speech. And I think that, in the context of this workshop, obviously, there's a lot of overlap, and the notion of harm reduction is really valuable. So my question for you is, with respect to the conspiracy theories specifically, you had several slides there, and I think it's a really interesting problem, and I'm wondering whether you do anything to try to differentiate between, for example, bots from genuine users, because I think that given the documented, especially in the US, I don't know how it is in other countries, I don't want to speculate, but in the US, we have the Mueller report has kind of really demonstrated very clearly that that disinformation agents are trying to intentionally sow controversy, and they're doing it on both sides of the political divide, right? There were the Black Lives Matters, and then the the on the other side, of course, in the alt-right world. So I'm wondering if, is there any evidence that we can find, or how can we find evidence to differentiate between real people who believe these things, which definitely exist, and agents, whether it's bots or hybrid, like bot human farms from the IRA or what have you, that are amplifying this kind of conspiracy thinking with the intention of deliberately polarizing, kind of weaponizing the controversy. So would love to hear your thoughts on that.
Okay, there are studies that they show that actually bots are not the ones that spread mostly, false information. We are the ones. They can start maybe, but definitely there are studies that show that we are responsible for most of the propagation of false information. Say that, yes, definitely it's important to detect if some messages have been written by bots, especially in the first steps of the propagation. And Indiana University, they have a botometer that works pretty well. And but I think that, okay, this is part of the problem, but the problem is that we are the ones who propagate false information more than bots. They could be, they could certainly help in the first steps of let's say, of the propagation, but the problem itself is still there. So, okay, we can detect if some of these messages had been written at the very beginning by a bot, who knows from what country, just to speculate. But the problem, no matter who was the one at the beginning, this information and these conspiracy theories keep on circulating because of us.
Yeah, I agree completely that there are real humans that are underlying some of the challenges, but I think it would be, yeah, it's an open research question, and I think we should be keeping it in mind, but I appreciate your comments. And by the way, I'd love to see that reference that you're saying about the ratio of kind of bots to humans in these conspiracy theories, but thanks, I appreciate it.
Thanks, Ashiri.
Okay, Paolo, just one last question. You talk about fake news spreaders and hate spreaders and conspiracy theory spreaders. Do you think they may have some common pattern of behavior of independent, if it can be
yeah, interesting.
Kind of features?
Yes, interesting questions. As I said, this was the work on conspiracy theory propagator was a preliminary work, in the sense that, as far as I know, there isn't much done, no matter, okay, that we had the paper accepted, but a lot needs to be done. My intuition is that the narrative is different. I mean, the narrative in a conspiracy theory is more elaborated than in fake news or disinformation, whatever we want to call it. So there is a disinformation, fake news circulating that rely on a conspiracy theory. So, okay, some patterns could be similar, but I think that I expect a more elaborated narrative with respect to the conspiracy theory, with respect to false information or disinformation conflict. but I'm speculating. Of course, we wanted to carry out actually these experiments, but in the next future.
Yes. Okay, Paolo, thank you for your great talk. Thank you very much. So
Thanks again.
With the next presentation.
Okay.
Thank you,
thanks.
Paolo. Okay, in the next paper, it will be presented by the Yinglong Zhang. Okay.
Yep.
Okay, great. The title is User Polarization Aware Matrix Factorization for Recommender Systems. So, Yinglong, you want to start?
Yep. Okay. Oh. Can you see my screen?
Yes.
Okay. Hello, everyone. This is Wenlong. So today, I'm going to talk about user polarization aware matrix factorization for recommended system. This is the work I have done with my advisor, Alpha Nasori. Okay, so let's get started. So the first is the outline of this presentation. So first time we talk about the motivation, and after that, I will introduce about detecting the user polarization as our title has suggested. So after that is I will talk about the two method that we propose to counter user polarization. And then there's the experiment, and finally, it will be the conclusion. So, recently, study showed that misinformation actually fuels polarization, right? For example, fake news, conspiracies, they trigger the confrontation between two groups, and especially in the time of social media, right? So fake news, conspiracy can be easily spread and quickly. So research also find out that polarization actually leads to more misinformation. So people tend to sometimes they create even more fake news or misinformation to confront the other group and to or even to convince other groups, right? So at the end, there's kind of a loop formed, right? So this loop actually make the situation even worse. So this gives us the motivation to tackle this problem. So our work is actually inspired by Dr. Amasa Badami's work. So in their work, they focus on the item polarization. So they first introduced the machine learning model to learn the polarization score for the items. So as is showing here on the right bottom of the figure, one of the item has very extreme, ratings, 11155. So, and after they developed that machine learning model to quantify the item polarization, they developed several technical to tackle that item polarization problem. So for us, for this paper, for this work, we focus on the user polarization. So basically, we are trying to look at the user rating patterns. For example, on the left side of this slide, so the user has very extreme ratings, 115 Basically, it means that this user is give very low ratings or give very high ratings. So intuition behind this work is that we wanted to reduce the extremeness in the user's rating by transform the ratings to a non-polarized ratings. For example, we have 1, 1, 5, 5, 5, and then after data transformation, we will get a 2, 2, 5, 4, and 4. But this data transformation is based on the polarization score, how polarized that user is. So the first thing that we is that we have to detect and quantify the user polarization score. So what we have done here is that we use a pre-trained machine learning model to score the user rating patterns that I have shown before, and then I finally for each user that will be a polarization score is between 0 and 5, and the machine learning model that we used here is actually the same style as the paper as the work from Dr. Abadami Massa. So we just retrained that model on our new data. So as I mentioned before, the intuition behind this work is we want to reduce the extremeness of the user rating pattern. So after we hope that after we do that reducing, the user now will become less extreme, and so they have chance to recommend some common items with other users. So you can see in this figure, we kind of put this two users together in the latent space by reduce rating extremeness. So now here is the first method that we proposed. It's called a user polarization aware matrix factorization. So as I mentioned before, we wanted to reduce or adjust the ratings of the user based on your polarization score. So here the phi EU is the polarization score, and the RUI is the rating for that user, and the delta is the threshold. So as I mentioned before, for example, in a rating scale from 1 to 5, the delta will be 3. So which means that if your ratings is bigger, is smaller than 3, we wanted to increase adjust your ratings or increase a little bit by the your polarization score. So on the other hand, if you are large, then the threshold here is 3, then we will reduce accordingly based on your polarization score, right? So after we do the data transformation, then we will do regular matrix factorization. As I show here, this is the objective for the matrix factorization. We basically wanted to learn PU and QI, which minimize this objective function, and the RUI comma is the one is the rating after transformation. So we do the gradient descent, and here's the updating rows after. So we hope that after actually this is what happened after the transformation. So this is a real user rating. So you can see this user rating is pretty polarized, extreme. So after the transformation, then they are concentrated on the middle. So that's what we actually are looking for. So the next method that we have proposed is that, so instead of just using the transformed ratings, we wanted to give a chance to the original ratings, right? So so in this modified objective function, that instead of just using the transformed ratings, we also plus that 1 minus the phi EU times original rating. So basically what I want to say is that we wanted to combine both. And if a user is very high polarized, as you can see, 1 minus phi U will be very small. So basically when the user is more polarized, that this objective function will lean more towards this transformative. ratings. So the same thing after we do gradient descent, we get an updating rule here. And all the details are in the paper. If you're interested, you can check the details. So now here is the experiment. So in order to test this, our algorithms that we use this data is called just the data set. It's about jokes. So so originally it had a 4.1 million ratings by 73,000 users and 100 jokes. So after we fill out of the some non-polarized user and the users that rated too few items, we end up with 1,000 user times 100 items. And then after we get the data, we do the training ties this splitting, and then we run 10 times. And others just the parameters for the different metric factorization. The method that we use to compare is we are considering several of them. The first one is called bias considered metric factorization. So in that paper, they assume that the user's rating is actually the sum of several parts. Like first one is the overall ratings of the average across all the users and items, and then the user also user biases is the average of the user ratings. The item bias is the average item ratings, and then they basically just learn the bias, like Q and P. So and then they add all them together and consider that as the the user ratings. So and then we also come the second one is the method that we propose is called user polarization aware metric factorization. And then the third one is that after we do the transformation, we also want to say, okay, now after the transformation, we also wanted to check how about we use the bias consider metric factorization. So that's the third method that we use, and the final is the weighted user polarization metric factorization. It's based on the Polarization score. So now here are the metrics that we use. Like I think those are the widely used metric. The method to evaluate your algorithm. So I will not go into detail too much here, but I do wanted to mention the one of the metric that we use that is different from others. It's called blindness mode size. So basically, the blindness mode is like for one user, let's say we have 100 items with new predictions. How many of those items will fall into the blind spot, which means that you will never face. For example, if you only recommend the top 5, then 95 of them will not be seen by that user. Okay, so that is just for one user. So after we calculate the blind spot size for one user, we can do that across all the users for one time. So for example, if you think about this one user, one of the items that they how many times they fell into the blindness model across all the youth. So that's the metric that we used for our evaluation. So now here is the results. So as I mentioned before, right? So in our data, we have polarized user and non-polarized user, and that is based on the machine learning model, and then and a cutover with 0.5, right? So so in order to have a clear trend of the evaluation, we separated the polarized user and non-polarized user and calculate the all those metrics. So you can see the first is the MAE, that is a mean absolute error. So so you can see here basically what I want to show here is that by transform the user ratings, we did not sacrifice the accuracy in terms of MAE. So yeah, so here is the one that the method that we proposed. And the next, I think, is the let me see, is the novelty. Oh, I think it's in. Oh, NDC score, sorry. So the next one is the NDC score. The NDC score basically measures how accurate of your recommendation in terms of the ranking. As you can see, our method is among the top method that we are comparing. The same thing with novelty. Novelty basically means that among the predicted, among the recommended items, how many of them are not popular, right? So as you can see here, our proposed algorithm still are on the top. The same thing with the diversity. Diversity means that among all the recommended items, how far they are, how diverse of these recommendations, right? Our algorithms get fairly diversity score with other methods that we have compared. So the final is about the blindness mode. As I mentioned before, the blindness mode actually means that for one item, so for example, take this item 5 as an example. So with our algorithms, this item 5, has a fairly lower blindness BL score, blindness model score, which means that across all the users that we have in the data, we have like a 60%, let's say assume that we have 100 users, 60 of them are being recommended of this item. But if you look at the other method, like for example, for this one, for the weighted user polarization aware MF on the original ratings. So you can see they are fairly higher, which means that now this item fell into almost like 90% of the users fell into the blind spot across all the 90% of the users. So, and this is a regular MF. You can see it's slightly higher. And then this is a bias considered user polarization score with metric factorization. So overall, that we wanted to show that our algorithm actually achieve like a lower blindness score. So here's the conclusion, right? We in this work we proposed the two user polarization aware metric factorization to counter the user polarization problem in recommended system, mainly in terms of their metrics factorization. And the result shows our algorithm actually outperforms the some of the baseline of a metric factorization in terms of the relevance metrics, novelty, and the blindness score that we defined. I think that's all. Any questions?
Okay, thanks. Any questions? Oh, I wanted to ask you about how do you detect the polarization? It's only based on the ratings, isn't it?
Yeah. Yes, that's right.
Of the ratings, and there is some threshold where you say this is polarized, or?
Yeah. So so the way that we define we detect the polarization is is purely based on the ratings. So for example, we extract some of the features from the rating pattern. Like if the user is very polarized, you can see that there will be a lot of ratings on the left hand, and there will be a lot of ratings on the right hand. We collect some features. So for example, we use two Gaussian distribution to feed that data, and then get the Gaussian parameters like the sigma and delta. I mean the mean value and the standard deviation value. So you can see we use kind of a different technique to extract features, and that work is mainly being done in Dr. Masa Badami's work. So we basically just inspired by their work actually, and just use that how they define that feature, how they train the model. We just use the model to train on our own data and then get a score.
Okay.
Yeah.
Do you think that analyzing the items that are generating this polarization may enrich the technique or the algorithm? Seeing which are the items that are receiving so polarized or generating so polarized behavior?
So I was saying that whether the item polarization will affect our results, or
maybe just seeing the items in both groups and extracting some features or something may enrich
Oh, I see. That's a good idea, actually. But in this work, we only like focus on the user, user rating pattern, like how the user polarization score. We didn't think about like the item. But you are right. We definitely can kind of combine these two together. But that will be for the future work.
Okay. Great. Yeah. Okay. Thanks, Wenlo. Then we will continue with the next paper presentation.
Yeah. Thank you. Thank you.
Thank you. So the next paper will be presented by Rim Ben-Sanem. That's Rim. Rim's PhD student at the University of Montreal, and she will present in the paper The Privacy versus Disclosure Appetite Dilemma, Mitigation by Recommendation. Yes?
Hello, can you hear me?
Yes.
Okay, thank you for the introduction. So I'm going to be presenting our paper, The Privacy versus Disclosure Appetite Dilemma, Mitigation by Recommendation, which was co-authored with my supervisor, Professor Esmaimer, and our collaborator, Professor Hisham Hatch. Okay, so let's start with, this is the outline. Let's start with a bit of context and motivation. Nowadays, online attacks, like they're becoming a lot more prominent, from phishing to spear phishing and ransomware attacks. And this is in big part due to the fact that users often disclose too much information without actually knowing that they're doing it. So they have their public profiles on which they disclose a lot of information. They overshare in posts about their travel plans, their family situations, etc., which actually facilitates attacks, due to the fact that these malicious people can actually tailor attacks specifically to them. Okay, so if we take, if you consider some statistics, in fact, one study showed that 62% of people share good news on social networks, 39% of them share bad news on social networks, and 24% confess that they actually accept friend requests from whoever sends it. So like they end up having these quote unquote social media friends who are basically strangers that are able to access their privately shared information with their friends. So we think of these types of disclosures in general as things that maybe the younger generation does, or people who are not that aware of the dangers of these actions. But in fact, that's often not the case. As a matter of fact, what later on came to be known as the Privacy Project, it revealed that 12 million Americans had their data, specifically their location, actually activated during their entire day, which revealed some alarming records, including, just one second, including this example in this animation. of a senior Defense Department official who actually, they were able to track him throughout his entire day, and they were actually able to locate his home, his like friends' homes, etc., which shows one thing, that is a lot of people are susceptible to these attacks or to these types of behaviors. So, which brings us to the question, why? One explanation of this is the privacy paradox, which is basically the discrepancy between what people claim that they care for, what they actually might even think that they care for, and then what they actually, or how they actually behave. So they would say that they're worried about being monitored by governments and companies, but then they go ahead and they just gratuitously share information and maybe even every aspect of their lives on social media. So in one study, it was shown that when they surveyed 14,250 Alipay users, they were divided into two groups. So Group A claimed that they were very concerned about their privacy, and they were the majority with 85%. But then in a follow-up study with the same users, this group of people were actually more likely to reveal private information, even though they claimed that they're very concerned about their privacy. In this specific paper, what we consider to be disclosure parameters are three main parts. For one, we consider social circle, so people with whom this user or participant is going to share data, because that makes a difference. Then we consider the second thing, which is the drive, or what we call the appetite for disclosure, which is inspired by the risk appetite. And the third parameter is the sensitivity level, which depends on the type of data. So depending on what piece of information is being disclosed, it is of like varying degrees of sensitivity. So actually, this isn't like out of the blue. So we've done previous work on this, which coincidentally is actually something that we published last year in this very workshop. Previously, we discussed the general architecture of our system, where we would have a user who has a certain input. We have a module that we call the information extraction. It generates a sort of threat vector, which associates the disclosed information with the degree of severity. And then we have the recommender system here on the right, which takes as input that threat vector, as well as some domain knowledge and user model. So in the user model, we have user-specific parameters that help in personalizing the actual recommendations. A bit of zoom in on this. We had previously like three modules in the recommender system, and they taken that threat vector, and they considered two parameters as input, some objective, what we call objective risk assessment, which is actually what is referred to as the non-user specific values, and we have the user specific view of their privacy. And then we generate these recommendations, and we have the feedback to further adapt the system. This is the general risk function, the general risk function that we had at the time, where we would multiply a weight or the risk by a function of disclosure. So how much of this information is being disclosed? Is it fully disclosed? Is it not? And that would give us an idea about the entire disclosure related to a post, let's say. When it comes to this new model, we are still actually trying to balance two things, which makes sense. We have a user-specific parameter, this user that is actually that wants to commit the disclosure, they have their drive to do so. And we have another parameter, which is the loss in terms of privacy, the deterrent from disclosure. So we actually considered the one special case of the item response theory, which is the Rash model, which is actually, it computes the probability of an outcome in, and takes as an input two parameters. So we have the individual ability and the item ability. So basically here we're trying to compute the probability of an individual actually doing a certain action. And in doing so, well, usually we do it with tests. That's why we have like item or question difficulty. So how likely is this person or participant or like test taker, how likely are they to respond correctly, given that they have a certain ability and that the question is this like a level of difficulty. So we were inspired by this because it's actually applied to a lot of disciplines and a lot of fields. So we used this basic like Rash model in our case to model the disclosure of a piece of private data. So we still have like two parameters, one the user, their drive for disclosure, and another parameter which is the sensitivity, what should stop like the user or maybe deter them from the disclosure. And this probability that we compute here is the probability of disclosing a piece of private data, which is actually what we want to stop the user from doing. That's why we, well, another way to phrase it is like the opposite outcome, accepting the recommendation to mitigate the disclosure and not proceeding with that disclosure. So it's pretty much the same thing, just reverse these two, like the beta and the delta value. So one thing to consider is what does this beta value actually depend on? It depends on the person themselves, first of all, on their perception of their privacy and the environment. So for example, we have a person on the left who said that they don't want to actually reveal too much of their private life because their company like wants employees maybe to remain too professional in a way. And we have a different person who is in the same situation when it comes to their frustrations, but they actually feel more encouraged to do it. So this like different circumstances make the beta value vary. Another thing is when we consider the same person revealing the same information, depending on to whom they reveal it to, that could actually make a difference. So if they're about to reveal like something like their political opinion, they might feel comfortable doing so with their friends, their close, like real friends and family, rather than their boss or colleagues. So following that, we actually divided our what we consider to be our social context in this paper into three parts. So we have the close friends and family, we have the colleagues, and we have like general public. And the same user is going to have different like disclosure appetites dependent on these contexts. So if we consider the recommendation process as a whole for our entire model, what we do is that we estimate the disclosure appetite, the beta value, and the data sensitivity, which is the delta value. Then we calibrate the model as we learn more about the users. And finally, we personalize our recommendations using the Rash model. So these are the different steps. How we do it, like practically, we proceeded with a survey that is that has three different sections. The first section is a self-reported privacy concerns, where we tell users to estimate what they think about their data, each like specific piece of data. Then in section 2, we give users context-specific scenarios, and we see how they would actually behave in specific scenarios rather than a general statement that I care about this piece of information. And then we proceed with the recommendations. So an example of this, for example, if we ask people to, like, would you share your health-related information publicly as a general statement, what we found out is that most people would say, no, I would never do that. This is very important to me. And then if we follow up with a specific scenario where we tell them that you, for example, you have a specific illness and you would like to share these, like some routines and health-related information that you, that are related to you, and we ask them about public setting, they would, like a lot of them, in our survey would actually answer in a different way to compared to the first section. if that happens, so in the third section, we would actually proceed to remind the users of what they disclosed previously, what they said about like how they value that, and that would be part of our recommendation. So these are the three sections. So moving on to the detailed process. So our survey is divided, well, not the survey itself, but rather the answers. We had 800 participants. So amongst those, we divide them into two batches, one that we use to estimate and calibrate the model, and the second one we use to test and evaluate the model. So when it comes to the first batch, as we said, that the first step is the estimation. So we compared different estimation methods from the joint maximum likelihood estimation, the marginal maximum likelihood estimation, the conditional one, and the pairwise maximum likelihood estimation. And we compare them in terms of the root mean square error, as well as the reliability, which is an indicator of how well the model would generalize. And then we have another measure, which is the global fit for both measures, for both the data sensitivity and the disclosure appetite. And the joint maximum likelihood estimation method was the one that outperformed the others, which is why we picked it. Then we move on to the calibration, so which we're still with the first batch. And at this point, what we want to do is to calibrate the model based on what we got from the first estimation. So we have these observations and we've got these beta values. And then we want to calibrate the model, but also obtain some estimations of the data sensitivity, the delta value. What we use with that, well, what we do with that is we wanted actually to establish some updated version of this onion model structure, which was introduced in the social penetration theory, which is the theory that explains the development of relationships as a function of how people reveal information and how in-depth their relationship gets. So they actually do present the different layers of personal data or of private data, going from the outer layer to the inner layer in order of sensitivity. So layer 6 here is the most sensitive one. We want to update this in coherence with nowadays. So what we did was, so what we did was we actually took the output of our calibration method, and what we did is that we took the categorization of the delta values, and we obtained some upper bounds which define different categories that we use as our layers. So we obtained this model where we actually keep the presentation going from the outer to the inner layer in terms of increase in sensitivity, and we have a lot of pieces of data that we actually categorize into each part or into each layer. So moving to the testing, this is done with batch 2. So what we actually did was we actually wanted to validate for once the use of social context. We wanted to see if it makes much of a difference whether we use one beta value across all contexts or whether we proceed with what we have done, which is consider 3 different contexts. And we found out that users are more likely, or more like the model is more likely to fit with the users' views and their preferences if we consider different social contexts, which is our graph to the right, compared to the one to the left. This was one of the tests that we conducted. Another thing that we considered was how well our recommendations are received across different types of users belonging to different demographic criteria. So we considered North America and Europe. Well, these are the participants. We had participants from North America and Europe, and we had different age groups going from 18 to 45 plus. And we considered also students versus non-students, and we had different results across all the sensitivity layers. So in comparison with our previous approach, we actually compared the accepted or the ratio of accepted recommendations previously compared to this research, and we noticed an increase from 68% to 77% of acceptance, which is good, but it's also encouraging us to explore whether this would be the case for other areas, for example, other than Europe and North America, and whether other considerations for context are needed. So yeah, finally, we move on to the conclusion. So self-disclosure, which is the act of revealing information about oneself, it's actually one of the major catalysts of cyber attacks. There are multiple reasons for which users might proceed with disclosure, but like our approach is not to tell them not to disclose any piece of information ever, but to find some balance along the way. And when it comes to our future perspectives, future work, we actually want to consider the risk of disclosure, like over time. What happens if this person keeps disclosing this piece of information? Does it retain its value? How to compute that exactly, and actually how to go or whether we should go beyond the social context, whether we should consider if maybe the location or the time or the emotional context of the person is of impact on their disclosure behavior. And finally, it's a consideration of multi-party privacy, which is basically the fact that we should shed light on the importance of not revealing information about someone else. So if someone shares a selfie with someone else in the background, they're actually revealing their information, and that should be taken into consideration as well. So thank you for your attention, and I would love to receive your questions.
Thank you, Renu. Anu, if you want to do your question.
I'm sorry, but the voice is very faint. I'm going to try to increase the volume.
Okay, Anu asks, what's the size of the data? For instance, how many users participating in the survey?
Could you I'm sorry, I couldn't hear you very well.
Very hard to hear you, Daniela. Sorry, I don't know if something may be wrong with your microphone.
Yeah, I'm struggling a bit. I don't know if it's on my side or yours, but I can.
Sorry, now?
Yeah,
much better.
Yeah, okay. Better. A lot better.
Okay, Anu was asking about the size of your data and how many users participated in the survey.
Okay, so we had 800 participants, 400 of whom from North America and 400 from Europe. That's the size that we had at this point.
Okay, and how do you get the parameters beta and gamma or delta from that survey?
Actually, we gave users a scale that they can rate their answer on. So they would say, for example, I value my piece of like this piece of data, I don't know, for example, 5 out of 7. And then when it comes to the scenarios, they would also respond with the likelihood of that happening. So we'd have numerical values to associate with scenarios and responses.
Okay, any other question? How much interventions or feedback from the users you need to associate the items to these categories you have?
Actually, we had one comprehensive survey. So each user had around 40 scenarios to respond to, and like those scenarios were used for our tests. So we didn't, well, we followed up with them for a different reason, but we didn't really keep following up with users like for different iterations. That wasn't how we conducted the survey, because it was a bit hard to do also on Mechanical Turk to keep going to the same users like in different iterations.
Okay. Olfa, you want to?
Oh yeah, thank you, Reem, for this amazing talk. So can the survey data and the inferred models and the parameters be used perhaps to build larger scale simulations, maybe to help with some of the future work?
Actually, we're thinking about that. We're thinking about it like as we accompany like that by another thing, which is we want to have a simulation in real time that would actually be able to detect these people's disclosure. So you'd, for example, be able to access an interface, and you would be able to type some text. The disclosure detection would be in real time, and that would be used to like paint a bigger picture of disclosure. So if, for example, someone discloses this piece of information, there could be given statistics, maybe 80% of people are actually likely to fall for this and to disclose this piece of information. So that is the end goal, is to raise awareness and to make people actually realize how much they disclose without knowing how much they disclose.
Thank you. Thank you. And if I can follow up, whether I know Paulo already mentioned personality inference, right? And whether that can also be used to try to infer if there is a domain that somehow, for some users at least, right, that could be correlated with the personality types, you know, the disclosure. Whether that's something you could look into.
Yeah, actually, we don't have like a published work on this like as of yet, but we started to explore, for example, whether a person who displays a high level of agreeableness, let's say, if they're more likely to be persuaded into maybe revealing a piece of information, or maybe they are more susceptible to bias, and if they see someone else revealing a piece of information, they think it's okay, and they do it as well. So it's definitely something to explore. It's very interesting to correlate like personality with the disclosure behavior.
All right. Thank you so much. Great talk.
Reem, last question, what applications you envision for your work? I mean, in what scenarios you can add this? Actually,
we want to have our system as some sort of companion to users as they navigate social media. It would be some companion on their side. Of course, we have some issues to consider with this, like also the ethical implications of maybe monitoring people. We need to make people aware of this. We need to get people to agree to having this companion on their side constantly, which isn't necessarily an easy thing to do, but that's the goal. The goal is to have this like assistant of sorts to be always like there for people to help them.
Okay, so thank you for your talk, Reem. We'll continue. Thanks. We will continue with the next paper presentation and the last one. Felice Antonio.
Yep, I'm here. Can you hear me?
Yes. Okay. So Felice Antonio Mario is a PhD candidate at the Polytechnical University of Bari, and he will present in the work Personal Attacks Against Visual Recommendation and Investigation on the Influence of Items Popularity. So please.
Yeah. Can I start? Thank you for the introduction. Okay, thank you everyone for being here. I'm presenting here the work Adversarial Attacks Against Visual Recommendation and Investigation on the Influence of Items Popularity, a joint work with Walter Anelli, Tommaso Di Noia, Eugenio Di Sciascia, and Daniele Malatesta from Polytechnical University of Bari in Italy. We already know what are recommender systems. We are in the RecSys community, but what it is interesting is that in some of the recommender system, like in the fashion domain, also point of interest domain, there could be the importance of visual. Indeed, visual recommender systems are inside the class of content-based or hybrid recommender system, since they can use some type of additional source of information like audio track or product images that can be integrated into the system in order to improve the recommendation performance. Basically, the concept is to exploit this hidden signal to make the model more reliable in the recommendation task. Indeed, this work is focused on visual-based recommender systems. So we are considering the class of recommendation systems that are going to use product images. The general approach assumes that we have the picture of a product, we extract features generally with a pre-trained convolutional neural network, and then these features are mixed together the collaborative signals that comes from the classical user item interaction in the recommendation platform to build visually aware recommendation list. However, in the last year, while we are talking about images, we should also take into account the advances of adversarial machine learning in the computer vision. Indeed, adversarial machine learning is a quite recent field of study in the machine learning community that is more dedicated to the study of securities and also possible attack scenarios. This here is a classical example that we can mention in the community, where given a picture of a panda, the addition of an imperceptible perturbation named adversarial perturbation make the image still a panda for the human evaluation, so it is human imperceptible. But the state-of-the-art classifier like ResNet 50 or ResNet 152 can misclassify that picture like with another animals, for instance, gibbon or dove. So in the case of recommender system, then the adversarial machine learning start to be spread across the different domains. First of all, with the injection of end-engineered attacks, named also shilling attacks. That is a field of study that started already 20 years ago, but recently gained more attention, above all because we had the integration of machine learning engineered shilling attacks. Then there is also another field of study inside the adversarial machine learning recommender system, the ones on model parameters that we will not be analyzed during this presentation, and the ones on the attack against multimedia recommenders. So the goal is to perturb the content of the recommender system. And here, basically, the question that we had at the basis of this work is, can visual recommender system be altered by adversarial attacks? And this type of question has been recently answered with the two main lines of work. One is related to testing time attack or also evasion attack. In this setting, the idea is that given a visual recommender system, we assume that a seller, for instance, on an e-commerce platform can change the picture uploaded of their products in order to modify the behavior of recommender model that has been previously pre-trained on a training data. So we are evading the classical recommendation task, and we will see later some of the main works. While at the training time, the idea is to upload from the beginning adversarial images, so that images that we have seen before that are misclassified by a machine learning model but are still human imperceptible in order to make the model not more robust against a particular items or a particular item or a particular set of items. And let's see in this case what happens with the testing time. The first work on testing time assumes that the adversary has a white box knowledge, and with the goal to break the integrity of the system, so the accuracy of the system, it adds adversarial perturbation on model parameters. Note that this is a white box attack. We are assuming that also the adversary can access the model parameters, and it is a bit not reliable as attack. It is not applicable in the real scenario. However, more real are black box attack models, like the one proposed by Cone et al. At Wisdom 2021, so this year, where basically he modeled the construction of attacks, considering the fact that the attacked images should change their prediction score and their position in the list. In this paper, the author proposed both white box and black box scenarios. Also, at WWW 2021, there has been another work on testing time attacks, where basically the goal is quite the same of the previous one, where basically the adversary can access the gradients of the model in order to backpropagate that gradients towards the original image, such that the perturbation is built to change the loss the loss of the model, the behavior of the model. So also in this case, we have a white box scenario. While on the poisoning, we have other works that are not related to this current work, but we are also the authors of this training time attack, where basically the goal is to upload the images of a particular class of products, I don't know, the shoes, that will be misclassified as a t-shirt in order to mimic the behavior of the t-shirt recommendation instead of the shoes one. And in this case, there are also analysis on how we can protect this model with the current state-of-the-art computer vision techniques. However, in the current work, what we are trying to answer to a novel research question that I have not been investigating until now in the community when we are going to analyze adversaries in the case of content-based recommender system or hybrid recommender system. So what is the effect of items popularity? With respect to both the increasing of the preference scores, so in this case, we are assuming that the adversary wants to push the attacked products in the top key recommendation list, but also the position itself. And as a methodology, we analyze the classical item recommendation task. We use as the basic model a baseline visual-based recommender model, which is VBPR, Visual Bayesian Personalized Ranking, which basically use feature extracted from a pre-trained convolutional neural network, which is ResNet 50, that recently has been demonstrated to be one of the best performing convolutional neural network for facial or visual recommendation tasks. And what we are going to analyze is our three set of attacks: a black box attacks, which is named TAMR. Basically, these attacks will be analyzed later, and two white box attacks, one based on the sign and one based on the backpropagation of the gradients. For this work, we have sampled 200 random target items from the entire catalog. Let's see the first type of attacks. The first type of attack should be the most difficult one, where basically you don't know anything on the model, and what you can do is to upload pictures such that the images will be classified from the convolutional neural network used to extract the classes and the features as another item. So basically, that epsilon is the magnitude of the perturbation, and the goal is to have a very small epsilon, like for instance 1 or 2 or 4 pixels, such that the perturbation is not human imperceptible. Because if epsilon is very big, then the perturbation is perceptible, and we are not no more in adversarial setting. While for the white box one, as you can see in this formula, we have the consideration of the model prediction function. In this case, indeed, what we do in this type of attack, it is a white box attack because we know the model parameters. We backpropagate the sign of the score function used by the recommender in order to maximize the preference score estimated on that item. So in this case, we use the sign, while in the model proposed by Zunal Liu and Morten Larsson, the goal is to use the gradient itself while we are perturbing the perturbation. And in this case, instead of multiplying by epsilon, we fix the perturbation inside epsilon. So epsilon is a norm ball around which each pixel can be modified. So after we have analyzed these three sets of attacks, we have obviously experimented them to understand what happens on the different items ranked by their popularity. To do so, we have used two common dataset in visual recommendation tasks. One is Amazon Boys and Girls, so we downloaded the dataset by my colleague on boys and girls classes. And the same we have done also for Amazon Web, which is a bigger dataset. We have more than 30,000 items. We measured the attack efficacy with the three metrics. One metric is for the analysis of the preference scores that we name prediction shift. So we have basically averaged for each target items the shift in the score before the attack and at the beginning, before and after the attack. And we have put a one value for the improvement fraction to analyze how many times the attack has been effective, and also for analyzing its effect on the top key recommendation list, we have used the iteration on top key. So we measure how much time the target item hit a top key list for each user, and obviously for each item in the set of items that we are attacking. So we go back to the researcher question that I presented before. So what we want to see in our results, or to understand it in our results, if there is an impact of the item's popularity. To do so, we have analyzed 4 groups of with the 200 items that we have sampled before. We have split them in 4 groups: in low popular, mid low popular, mid high popular, and very high popular. And we have computed attacks by varying the epsilon from 4 to 8 to 16, which are basically the number of pixels on which each pixel can be changed while we are doing the attack. Obviously, when we increase the epsilon, as you can see in the results, we will have attacks that are more efficacy. It is the reason why in the analysis of the answer to our research question, we focus only on epsilon equal to 4. And we can observe that when we move from the attack efficacy on low popular items is higher than the most popular one. So it means that the item's popularity is having an effect on the performance of attack. So low popular items are also this bad behavior. They can be more attacked by this type of attacks. Also, in addition to the fact that generally they have low recommended. And this phenomenon is also very present also when we are going to analyze the top key recommendation list. We have focused this time on the top 50 items recommended for each user. And in this case, also we can observe that in the case of low popular items, the attack has been much more effective. So they are getting too much variation when we have this phenomenon. So let's conclude this work. We have examined whether test time attacks can impact the visual recommender system, also considering the fact that the items are affected by popularity biases, basically, and we have explored both black box and 2 white box attacks with different perturbation budget, which is the epsilon. And the experiment have confirmed that the least popular items can receive a bigger increment on the preference score, making them more easy to be pushed in the top 2 recommendation list. So the idea is to extend this study to iterative adversarial attacks that have been demonstrated also in recommender system, but also in the computer vision to be more effective with the same adversarial budget, but also examine the potential effects if we move our attention on the user's activeness. So user more active, are they more affected by attacks? We do not still for now. And also verify effects then also with user study and human evaluation if they are able to understand when a strange item is appearing in their top key recommendation list when it is attacked. So thank you for your attention. We are releasing the code on the Elliott framework, and these are our content. So for any question, I'm happy to answer.
Thank you, Felice. There is no question. I would like to ask you if so now that you verify that items popularis influence the attacks, if you have thought about how to defend from these attacks based on popularity. Items popularity.
Thank you for the question. Yes, we are thinking about the possible defense that are taking into account this phenomenon. And basically, one of the idea is to use, for instance, oversampling, in the sense that when we are using a defense like adversarial training, instead of focusing in a fair way across all the items, we should put more attention the items that are less popular in order to make a defense that is able to avoid this unbalancedness of attack effectiveness. It can be an idea, for instance.
Anu, if you want to ask, listen.
Yeah, so I have a question regarding the level of item popularity. So yeah. How is the different level of item popularity is measured? Is it based on rating, like if 1 it's low popular or like 5 high popularity? What is the method of measuring this item popularity?
Thank you for the question. Yes, in this case, what we have used is the number of feedback received by the items in the training set. So in the set of the target items, we have ranking these items based on the number of feedback received in the training. And the low popular are the first 50, then from the 51 to the 100, it is the mid-low popular, and the most popular one on the last class. So the one that got the highest number of feedback in the training set. So it is based on the ratings or feedback, depending on the data that we are using. For instance, in Amazon, we have reviews as the implicit feedback.
Mm-hmm. Okay, thank you.
You're welcome.
Any other question? Olfa?
Yeah, mine is more like a comment. Thank you so much for the great talk, also, Felici. So I was just, I'm sorry, my dog is making these noises with the toy. So the low popular items, we know that they suffer from unfairness in terms of exposure, right, in general. But you also found that they're also more affected by attacks, right, compared to more popular items. And it doesn't matter which direction, whether to push them up in the ranking or down in the ranking, right?
Yeah. Basically, this yes. Thank you for the question observation. Yes, basically, we are observing in this case that the item popularity bias is having a bad effect also on the robustness side. So it raises also novel possible question on item on when we have this phenomenon of popularity. We should also take into account only the fairness aspect, or we have also to start to think about how they can be attacked, for instance. So we can also talk about the fairness in the robustness. It is something quite new in the community thing.
Yes, so, yeah. Thank you.
Yeah.
Just one last question. How is the user perception of the attacks? Do you think they can affect something?
Thank you. First of all, yeah, basically we have done a study using in another article that for the one that are interested, I can point you. Basically, we have studied different human evaluation based offline metrics, like for instance the LPIPS, which is a metric that measure the human the capacity of humans to perceive the difference in images. And we have observed that basically these images, above all when the perturbation budget is low, are not perceptible. So basically the user are not able to understand if that picture has been perturbed. However, what can be, in my opinion, interesting to explore is that they also able to understand that the recommendation lists that they are getting are quite different from the one that they should expect. For instance, if you like a lot running shoes and we are uploading socks that are adversarially perturbed to be considered from the system as running shoes, and you start to see socks in the top 5 recommendation list, is this strange behavior be a signal of alert for of danger for users? So a human study should be interesting to analyze if they feel a bit uncomfortable when there are these type of attacks, because these attacks basically are quite imperceptible also from a machine learning perspective. Because if you put a detector, for instance, you can build an attack, a white box attacks that evade the detector and then evade also the recommender. While humans at a certain point should be able to understand if the recommendation lists are quite strange. And it can be, for instance, we can put a button on the page saying, I feel that this image, this item should not be here. But it is something that is an interesting direction, I think, to be explored in the future.
Okay, great. So thank you, Felici, for your talk.
Thank you very much.
Thank you. So just a few words to closing this year edition of the edition of the workshop on online misinformation and hardware recommender systems. We, Antonella, Arcais, and I, we want to thank all of you for the participation in the workshop. Many thanks for your active participation. To the paper presenters, also especially to our 2 keynote speakers, Alexandra and Paolo. Thank you very much. We appreciate your contribution to the workshop. And also, we want to thank the workshop co-chair of RecSys for giving us the possibility of hosting this workshop here at this great conference. And also we extend this thank you to the General Chase for this amazing conference organization. So we hope you can see you all next year in the 3rd edition of the workshop. And thank you everyone for being here today.